Hello everyone, the slides are visible. Hello.
Yes, sir, they're visible.
Okay. So before we start today's class, some corrections. In the last class, some mistake was there in this last equation which is there in this slide. Okay, so 1 by u naught is given as 1 upon this entire bracket. That is what is been given in the last class, so that is corrected here. So 1 by u naught and 1 by ui, these are given by the corrected equations which are shown in the slide now. Okay, that is just a small mistake we did in the last class. Other than that, one more thing I wanted to clarify here is whenever we are looking at the biot number as we have done it in this problem. So we find out the biot number in order to understand whether there is a internal resistance present inside the solid or not. So whether we should neglect that internal resistance or not, for that we find out the biot number. In all such cases, we have to use the length here as a characteristic length which is defined as volume by area. Okay, it is defined by volume by area. So for a flat plate, it comes out to be just L. For a cylindrical case, it comes out to be R by 2, and for the sphere, it comes out to be R by 3. So this you have to remember, and this characteristic length here is used only for finding the Biot number. For example, here this area which we are using in the heat transfer, that is the actual heat transfer area we are looking at, isn't it? It's not based on the characteristic length. Okay, so this characteristic length is only used to find out the Biot number. Okay, that's it. So these are the two corrections which we missed in the last class. So let us summarize what we have done in the last class. So we started with the concept of heat transfer coefficient, isn't it? So until now we were only looking at the heat transfer by conduction, and since you are aware now that by every passing class we are including some difficulties in our analysis. So in the last class we started looking at the heat transfer coefficient, because in order to quantify the heat transfer, not only the conduction is important but also convection is important, because conduction and convection both are in general present together. Okay, isn't it? So heat transfer coefficient, concept of heat transfer coefficient becomes important here. Again, unlike the thermal conductivity, heat transfer coefficient is a phenomenological coefficient. It is not a fundamental property of the material, isn't it? And it accounts the effect of thermal conductivity, it accounts the effect of viscosity, density, and medium. Okay. So again, the concept of heat transfer coefficient is very important here, because that enables solving a difficult problem with much more ease if we do our analysis in terms of the heat transfer coefficient. Because otherwise what we have to do is, since the convection becomes important whenever there is a fluid flow is there, isn't it? So clearly, in order to solve the problem, one need to uh, first solve the velocity distribution, and then we have to incorporate that velocity distribution in heat balance, isn't it? Which in general becomes cumbersome mathematically, isn't it? So this can be avoided by using the heat transfer coefficient which accounts the effect of thermal conductivity, viscosity, density, and the effect of velocity in it, isn't it? And this heat transfer coefficient is obtained using the correlation, so that we will see later on when we are looking at forced convection and the natural convection. There we will look at several correlations to calculate the heat transfer coefficient. But for a time being, what I wanted to say here is, by using the concept of heat transfer coefficient, we don't need to look at the uh, momentum transfer problem, and we can just directly go ahead with heat balance, and the heat transfer coefficient we can find out directly from the correlations which are based on the experimental results. So our analysis becomes simplified. We don't need to solve a complex problem involving a coupled heat transfer with momentum transfer. Rather, here we are looking at only the heat transfer problem, and the effect of this momentum transfer and other things is embedded directly in this coefficient H. Okay, so that was the background. Again, some problems we have solved in the last class. Okay, again, one of the important concept which we have seen in the last class is the overall heat transfer coefficient. Remember, whenever we are looking at the conduction, the Fourier's law of heat transfer is used. Whenever we are looking at the convection, Newton's law of cooling is used. But as I said, conduction is always associated with convection whenever we are looking at the heat transfer taking place through the fluids, isn't it? Because of the heat transfer, fluid never remains stagnant because of the density difference, or maybe because of some external velocity gradient. The fluid is always flowing, isn't it? So in such cases, there is a conduction and at the same time convection, and both these effects can be used by using the concept of overall heat transfer coefficient. So here you can see the overall heat transfer coefficient for a plane wall, which not only accounts, if you look at the system here, there is a convection taking place in this warmer fluid, there is a convection taking place in a colder fluid, and there is a conduction taking place in a wall. So all three effects are accounted using a overall heat transfer coefficient, and we can use a equation similar to Newton's law of cooling, but instead of small h, now we will use a capital U, which is nothing but a overall heat transfer coefficient. Okay, so that is what we have done here. Okay, so now for a planar wall this becomes easy, but when we go for a cylindrical wall, here the overall heat transfer coefficient is either defined in terms of inside area or outside area, because the area of heat transfer is varying as we move in a radial direction, isn't it? So even the overall heat transfer coefficient is defined in terms of either a inside area or a outside area. So here one thing to note down is Q is still given as U naught A naught Ti minus T naught, and it can also be given as Ui Ai Ti minus T naught. So here you can see U naught A naught is same as Ui Ai. So basically, to find out the heat transfer, which area should be multiplied, that depends on the coefficient, how we have defined the coefficient, whether it is defined in terms of internal area or the outside area, inside area or outside area, isn't it? Okay, so this is what we have seen in the last class. So is there any doubt, anything, or can we go ahead? Okay, am I audible to everyone? Hello.
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Okay, so let us start with looking at the heat transfer from extended surfaces. This is a very important topic because a practical example, if you could look at, many of you might have, driven the bikes or even the scooty, isn't it? So there you can, if you look at the engine of this bike, there is some corrugated surfaces are there just outside of the engine, isn't it? Some extended fin type of surfaces are there, right? So all these extended surfaces are in order to facilitate the better convection, higher convection rate. Okay, so if you look at, see, thermal conductivity of the gases is smaller than the liquid, isn't it, or solid? So clearly the heat transfer because of convection taking place whenever there are gases outside is slow. But can we improve upon this? That is the question we are asking here. Can we improve the heat transfer here? So the rate of heat transfer, see here we cannot increase the conductivity because that is the material property, isn't it? That is out of question, and the heat transfer coefficient outside in ambience, again, how much turbulence we can add. So there is nothing much we can do, isn't it? So heat transfer coefficient will be based on whatever the current is going outside the ambient in the air side. But the another way of increasing the heat transfer rate is instead of increasing the heat transfer coefficient, if we increase the area of heat transfer, still the total amount of or the rate of heat transfer is going to increase, isn't it? Either we increase the heat transfer coefficient or we increase the area of heat transfer. Remember, Q is given as UA or HA delta T, isn't it? HA delta T or UA delta T, depending on what are the different resistances present. Correct. So there is little we can do in increasing H. Of course, we can use the forced convection and all, but if we are looking at the ambient, that option is also limited, isn't it? So the another way to handle this is ultimately what we are interested in. Ultimately, we wanted to have a faster heat transfer. So that means we wanted to have a higher rate of heat transfer Q. So that can be either increased by increasing U or H, or if not, then by increasing the heat transfer area. So both are going to give me the higher rate of heat transfer, isn't it? So that is what the idea used in extended surfaces and fins. Here, instead of increasing the heat transfer coefficient, the focus is given on increasing the heat transfer area. If I increase the heat transfer area by having the extended surface, remember here you can see this is the extended surfaces coming out. So if I don't have this extended surface, I will have only this much area, isn't it? Only this much area B into W. That will be the area available for the heat transfer if I don't have the extended area. But in this case, when I am having the extended area, now my area of heat transfer is much higher, because now it is 2B plus W into L, isn't it? 2B 2 in the bracket B plus W, that is going to give me the perimeter multiplied by L, that is going to be the area. So clearly that area is much higher compared to the available heat transfer if we don't have the extended surface, isn't it? Maybe I just write down here so that things become clear. With no extended area, no extended surface, area is given as, area is just given as B into W, isn't it? That much will be the area.
So the whiteboard is not visible.
My slides are not visible.
No, sir.
Okay, let me just share it again. So we lost the connection just now, or it is quite a while?
Just now, just now.
Okay, okay. Okay, so can you see?
Yes, sir.
Yes, sir. Now it's visible.
So BW is going to be the area with no extended surface, and with extended surface, with extended surface, this is going to be two into L, isn't it? So this will be the area. Clearly, the area available for the heat transfer is going to be much higher compared to if you don't have the extended surfaces, isn't it? So clearly that is going to increase my rate of heat transfer. Is it clear? Is it clear to everyone?
Sir, in the extended area, extended surface, the BW term will also appear because that is also contributing to the surface.
The BW term here, isn't it? That is what you are saying?
Yes, sir.
Yes, you are right. You are absolutely right. Correct. Thank you for correcting. Yes. Plus BW. Correct. Okay. So this is the rationale behind looking at the extended surface, or this is regularly used whenever we wanted to have a higher rate of heat transfer in a gaseous side, in gas side. Okay, because the rate of heat transfer in a gas side is going to be low because of the lower value of thermal conductivity, even though we can have some external turbulence there, but still the heat transfer is going to be lower. In all such cases, the rate of heat transfer is increased by having extended surfaces in terms of fins. Okay. Now let us consider a thin rectangular plate that protrudes a distance L from a wall as shown. The extended surface or fin has a length L. Let's say this length is L, a thickness W, and a breadth B. The temperature of the wall here is T naught. I am just correct it. So here the temperature is T naught. Whereas the temperature of the ambient, sorry, this is TW, this is TW, this is TW, and the temperature of the ambient is somewhere here outside. Okay, so this is what the system is. Okay, just wait. Okay. So heat loss to the ambient occurs from both the surfaces. Here you can see the heat loss to ambient can occur from this surface, even from this edges also, 1, 2, and 3, isn't it? All three, the side faces also. As the thickness of the fin is small, we can assume that the temperature at any transverse section of it is uniform. Fin temperature varies only in the longitudinal direction, and heat transfer occurs through the fin by conduction in the same direction. Okay, so what is been written here is, even though the heat transfer is taking place from the top surface and the bottom surface, but we are not considering the temperature gradient along this transverse direction, this vertical direction, because the thickness of the film, thickness of this fin, we are considering much smaller compared to the length, and this temperature distribution along the vertical direction, that is been neglected. So only the temperature gradient is present along the longitudinal direction, that means along the x direction. So that is the assumption. That is the assumption. In real life case, we will have some temperature distribution, but we are neglecting, because the thickness of the fin is small. We are neglecting that particular um, part. Is it clear to everyone? So we are only looking at the temperature gradient or a temperature distribution along the x direction. We are not looking the temperature distribution along the vertical or a y direction here. Is it clear to everyone?
Yes, sir.
Okay. Let us look at the analysis of the this system. So let us now consider a thin section of the thickness delta x of the fin at a distance x from the base. So what we are doing is we are assuming a shell of thickness delta x, uh, uh, delta x, uh, which is this along the x direction, and why we are assuming a shell balance here? Remember, whenever we are looking at the plane wall and when there is a cross sectional area is not at all changing, we don't use a shell balance, but here we are using a shell balance. So can you say anything on that, why we are using a shell balance here?
Because there is a temperature gradient in this direction.
Because there is a continuous dissipation will take place as we move along the x direction from the top surfaces, isn't it? And therefore the temperature gradient dt by dx is going to vary. So qx is going to vary as we move. It is not going to be the same, isn't it? And therefore we are using a shell balance, and that is depending on what location we are looking at, qx is going to be different. Okay, that is why we are using a shell balance here. Clear? Okay. So again, for the breadth of B of the fin, the available area for heat conduction. Now we are looking at only the area for heat conduction. So area for heat conduction is going to be this cross sectional area, isn't it? This cross sectional area, which is nothing but B into W, correct? The heat transfer area for the convection will be all this, isn't it? But for a heat transfer, for a conduction is only this area, cross sectional area of this. If you look at from this side, whatever the area we see, this shaded part, this is going to be the cross sectional area available for the conduction, isn't it? So that is what BW. Area of heat loss by convection from the expose. So the area for the convection is going to be P into delta X, P into delta X, isn't it? And remember what we are assuming here is, so convection area is going to be this area, this side areas, and also this area is also available for uh, the uh, heat transfer, isn't it? Okay. Okay, so now rate of heat input at X will be given as the rate of heat input at X will be given as uh, if remember here in this case P delta X we have used, but we have not used in this case we have not used this BW additionally here, isn't it? Why? Because only we are looking at this shell. For this shell only the areas available for the convective heat transfer is this area and on the opposite side. So this side area is not available when we are looking at this particular shell, and that is why this additional plus BW is not being used here. So area of heat transfer for convection for the shell is going to be only P delta X, isn't it? Where P is 2B plus W. Is it clear to everyone? Isn't it? Is it clear?
Yes, sir.
Okay. So now let us make a shell balance. So rate of heat input at X is given as BW, that is the heat transfer area for conduction into QX, and that is calculated at the location X. Rate of heat input at X plus delta X is also going to be BW QX, and that is calculated at X plus delta X. Rate of heat loss from the exposed surface, so that is the amount of heat loss from the element by a convection, and that is given as P delta X, that is going to be the area of heat transfer for convection into heat transfer coefficient H into delta T. So where T is the temperature present at that particular location on the fin. So this T is nothing but the temperature of the fin at the location X minus T naught, where T naught is nothing but the ambient temperature, isn't it? So P delta X H into T minus T naught is going to be the rate of heat loss from the exposed surface at the element. Okay. Again, rate of heat accumulation we are assumed 0 here. So then we can make a shell balance. So shell balance in this case is going to be input minus output minus heat loss, that is going to be equals to 0. So I have forgot to put it 0. I'll just put it 0. Just wait. So this is 0.
Your screen is not visible now.
Still lost. Okay, I'm just adding. Is it visible now?
Yes, sir.
So this heat balance, we can have BW QX at x minus BW QX at x plus delta x minus P delta x H T minus T naught equals to 0. So we can divide this entire equation by BW delta x and put delta x tends to 0. Delta x tends to 0. So what we get is, by doing that, this anyway we have done it several times. So what we are going to get from this is minus d by dx qx should be equals to ph divided by bw t minus t naught. Okay, so this is the equation which we are going to get. This is the equation we have obtained from the shell balance.
So there should be a 2 in the heat loss from the exposed surfaces, because
So
the
this 2 we have already used as a p, isn't it? Remember?
okay, okay, sir. Okay. Got it.
Okay, so this is the equation which we have obtained. Now let us try to solve this equation by putting some relevant boundary conditions here. So this is the equation number 1. Now in this particular equation we can further simplify this equation by putting the Fourier's law of heat conduction. So the heat flux along the x direction can be given as minus k dt by dx, and also we are defining t minus t naught as t bar. So this t bar we are defining as another variable. So if we put it in this equation, what we get is d square t bar divided by dx square, and that is equals to ph by kb w t bar. Now here ph by kbw, this we have represented by using another variable uh, as zeta square. So zeta is given as under root ph divided by kb w. So ultimately the equation which we get is d square t bar divided by dx square is equals to zeta square t bar. This is the equation. Equation number 2. Now we can put the boundary conditions here. So boundary conditions are at x equals to 0. So that is the base of the fin. At the base of the fin, I can go back at the base of the fin here. So temperature is going to be TW, isn't it? So that is the temperature of this vertical wall. Correct. So at x equals to 0, T is TW, and therefore T bar will be given as TW minus T naught. TW minus T naught. That is going to be at x equals to 0. The another boundary condition is at x equals to L. So that is the end of this particular extended surface. So we are looking at this particular end. So uh, at this end, we can have a convective boundary condition. So whatever the rate of heat conduction is at this boundary should be equals to the rate of dissipation by convection, isn't it? So the convective boundary condition we can put it here. So that becomes at x equals to L minus k dt by dx. So that is the heat flux should be equals to A equals to H T minus T naught. So that is, this is the rate of heat conduction, and that should be equals to the heat dissipation by convection. So H T minus T naught. So that in terms of T bar, we can write that as minus K dt bar by dx, and that is equals to H T bar. So equation number 4. Is it clear to everyone? Okay. Now let us try to solve equation number 2. Equation number 2, which is d square t bar by dx square, and that is equals to zeta square t bar. So the solution of this equation is obtained as, solution of this equation 2 is obtained as t bar is given as c1 cos hyperbolic zeta x plus c2 sin hyperbolic zeta x. That is equation number 5, and we can now apply the first boundary condition, that is equation number 3. So at x equals to 0, this cos hyperbolic zeta x, this becomes 1. So this becomes c1. The second factor sin hyperbolic zeta x becomes 0. So that goes away anyway. And t bar is given as tw minus t naught. So tw minus t naught is equals to c1. So the first constant c1 is given as tw minus t naught by putting the first boundary condition, which is given in equation number 3. Now in order to apply the second boundary condition require dt by dx, isn't it? We require a dt by dx, so we can differentiate equation number 2 with respect to x. So if we differentiate equation number 2, equation number 5 with respect to x, so dt bar by dx can be obtained as c1 zeta sine hyperbolic zeta x plus c2 zeta cos hyperbolic zeta x, and we can multiply this by minus k, and we can put entire thing in this equation number 4. So minus k dt bar by dx equals to h t bar. So t bar anyway we know, t bar is given by this equation 5. dt bar by dx, that is obtained by equation number 6, and this equation number 6 and 5 we can put it in equation number 4. So by doing that, what we get is minus k c1 zeta sine hyperbolic zeta l. Remember this equation number 4 is at x equals to L. So this x will be replaced by L there. So this becomes minus k c1 zeta sine hyperbolic zeta L plus c2 zeta cos hyperbolic zeta L in the bracket close, and that is equals to h t bar. So h as it is and t bar is given as c1 cos hyperbolic zeta L plus c2 sine hyperbolic zeta L. So we can rearrange this equation. Anyway, we know the constant c1. We can rearrange this equation and we can find out c2. So that is what is being done in the next slide. So everything is known here. Only unknown is c2. So c2 we can obtained as minus c1 k zeta sine hyperbolic zeta L plus h cos hyperbolic zeta L divided by k zeta cos hyperbolic zeta L plus h sine hyperbolic zeta L. And if we rearrange everything, what we get is minus c1 sine hyperbolic zeta L plus h by k zeta cos hyperbolic zeta L divided by cos hyperbolic zeta L plus h by k zeta sine hyperbolic zeta L. And this equation c2 we can put it in the original equation, in this original equation 5. c1 and c2 both we can put it in this equation number 5 and rearrange the equation. Remember here this equation is in terms of x, but c1 which is nothing but tw minus t naught, whereas c2 is given in terms of zeta L. Remember this is given in terms of zeta L. So if you rearrange all the common terms in terms of c1 will come out here. So that c1 will come out, and which will come in the denominator here. So that's why this becomes t minus t naught divided by tw minus t naught. Remember c naught, c1 is nothing but tw minus t naught, isn't it? Again, there will be a terms in terms of L as well as X. So common terms you can collect it. So that finally you will get is cos hyperbolic zeta L minus X plus h by k zeta sine hyperbolic zeta L minus X and divided by cos hyperbolic zeta L plus h by k zeta sine hyperbolic zeta L. So can you do it? Can you just see the rearrangement? Ultimately, you should get equation number 8. I have directly written it. So you have to collect sine and cos term, and then sine and cos term can be combined to this combined term cos hyperbolic zeta L minus X. Similarly, sine hyperbolic zeta L minus X. So these are the combined terms. Remember, isn't it? Is it clear to everyone? Is it correct? Hello. Background knowledge is good. Some background voice is there. Let me just mute. Okay. So is it clear to everyone? Hello. Hello.
Yes.
Yes, sir, it's clear.
So okay. So this is correct also, isn't it? Equation number 8. I have directly written equation number 8. You have to rearrange sine and cos terms before that, isn't it?
Yes, sir.
Okay. So this is what the temperature distribution. Now this equation number 8 gives me a temperature distribution as I move along the x direction. So here you can see as I move along the x direction, the temperature decreases. This T is going to decrease. This T is going to decrease with distance x from the base. So the surface heat flux from the fin also decreases. So that means dt by dx also decreases as we move along the longitudinal direction because the smaller temperature driving force is there. Okay. So rate of heat transfer Q. Okay. Now based on this temperature distribution, we wanted to find out the rate of heat transfer Q. Rate of heat transfer Q at the base. Okay. So rate of heat transfer Q. So if I go back, okay. So at this base, exactly at this base, when x equals to 0, Q, capital Q is completely by conduction, isn't it? Capital Q is completely by conduction. But as I move, there is a heat dissipation takes place. There is a heat dissipation takes place from this extended surface. So let us calculate a capital Q, which is nothing but the rate of heat conduction or a rate of heat transfer in this extended surface, isn't it? Correct. So we have to find out at x equals to 0. So that is why Q is written as BW, which is nothing but the cross sectional area exactly at the base multiplied by heat flux at the base. So that is minus K dt bar by sorry, this should be dt by dx. So it doesn't matter even if you take dt bar by dx or dt by dx, it is going to be still same, isn't it? So doesn't matter. So let it be. So minus k dt by dx at x equals to 0. So BW remain as it is, minus k is multiplied here, and this equation we have obtained. So we can differentiate this equation with respect to x. This t bar we have obtained. We can differentiate this equation with respect to x. So this TW minus T naught will come on the right side. So that is multiplied here into K as it is, and the differentiation of this is written here. And again, remember this is calculated at x equals to 0. So all the terms corresponding to x are here. This x will be 0, and then we can differentiate this equation. So what we get is minus zeta sine hyperbolic zeta L minus h by k zeta into zeta cos hyperbolic zeta L divided by this term is anyway is constant, isn't it? So this remain as it is. Is it clear? So by putting this differentiation and then putting x equals to 0, we get this. So we can differentiate equation number 8 and then put x equals to 0. So what we will get is this factor. So here this minus sign and this minus sign will get cancelled out. So what ultimately we will get is Q is given as BWK zeta TW minus T naught in the bracket sine hyperbolic zeta L plus h by k zeta cos hyperbolic zeta L and divided by cos hyperbolic zeta L plus h by k zeta sine hyperbolic zeta L. Okay, this is the equation. This is the final equation which is going to give me the rate of heat transfer Q. Now this is the rate of heat transfer Q at the base, isn't it? Correct. This is the rate of heat transfer at the base by conduction, and obviously this has to be same as the amount of heat dissipated from the fin, isn't it? So this Q, capital Q, is nothing but the amount of heat dissipated from the fin, isn't it? So amount of heat dissipated from the fin should be same as amount of heat input by a conduction at the base, isn't it? So if I look at here, the heat input by conduction here at the base should be same as the amount of heat dissipated by this entire fin. So that is nothing but Q. Okay. Now in general, for extended surfaces, the efficiency is calculated. The fin efficiency is calculated. So fin efficiency is defined in terms of what is the actual rate of heat transfer divided by maximum rate of heat transfer. So what is maximum rate of heat transfer? Remember here the rate of heat transfer is given by this Q, equation Q, where the actual temperature, if you look at, if I go back here, remember this actual temperature here at any location along the longitudinal direction X, this temperature here at the location X is going to be lower than TW, because there is a continuous heat dissipation taking place from the top surface, bottom surface and the side surface, isn't it? So the temperature here T is going to be lower. So clearly the temperature difference between the ambient, so that is T minus T naught, is going to get decreased as I move along the X direction. So the driving force for the convection is going to decrease as I move along the X direction, isn't it? Now what is Q max? Q max is a hypothetical concept. Q max is a hypothetical concept in which what we are saying that if the temperature along the longitudinal direction, if the temperature, this temperature here at any location along the longitudinal direction, if that temperature is maintained at the wall temperature TW, remember wall temperature TW is the maximum temperature available here, isn't it? So that is going to give me the maximum temperature gradient, temperature driving force, isn't it? TW minus T naught is going to be the maximum temperature driving force. So we are assuming that maximum driving force is available at all location along the X direction. So that is the hypothetical concept. Of course, this T is going to decrease as we move, but hypothetically the maximum amount of heat transfer can be obtained only if the temperature T at any location along the longitudinal direction will be same as TW. Okay. So maximum temperature, so maximum heat transfer Q max is defined as total area into heat transfer coefficient into maximum driving force. So maximum driving force in this case is going to be, I am just correcting it, maximum driving force. Okay. Is it clear to everyone what we are doing?
So can you please explain once why we calculated Q at X equal to 0?
Okay.
Was it?
Yes. Just wait. What is Q? Let us first look at what is Q. Q is the amount of heat heat transferred by the, remember, okay, maybe I just go to this. Okay, what is the aim of this extended surface? What is the aim of this extended surface? The aim of this extended surface is I wanted to dissipate the maximum amount of heat from this vertical plane, isn't it? So this vertical plane, whatever the heat is getting transferred from this vertical plane, maximum amount I wanted to get it dissipated to the ambient, and therefore I have used this extended surface. Now what we are saying here is capital Q is nothing but amount of heat transferred by this vertical surface to this fin, isn't it? To this fin. So amount of heat transferred from this vertical surface to this fin is nothing but what? Amount of heat transferred here at this location. So this fin is getting the heat only at this location, isn't it? Which is connected to this vertical surface. So since here it is connected to the vertical surface, the heat is obtained only by conduction, isn't it? So Q we have obtained only at this X equals to 0, isn't it? Now whatever the amount of heat obtained by this fin, that is getting dissipated from the top surface, bottom surface, side surface, and also this longitudinal surface here, isn't it? From all these surfaces the heat is getting dissipated, isn't it? So at steady state, whatever the amount of heat Q received at this location on the left hand side, exactly at the boundary where this the fin is connected to this vertical surface, by conduction is equals to the amount of heat dissipated by this extended surface by convection. Is it clear? Hello?
Yes, sir. Yes, sir. Yes, sir.
Is it clear?
Yes, sir.
Okay. So that is the reason why we are calculating here, because here only that takes place by conduction, isn't it? If I look at any other location here, there are two factors. There is a conduction as well as there is a convection, isn't it? Did you get it? Isn't
Yes, sir.
it?
Thank you. Yes, sir.
So the amount of heat that is getting transferred along the longitudinal direction plus the amount of heat dissipated till this point, both these factors have to be accounted if you look at the Q at any location here. But that Q also is going to be same as the Q here, because now I am going to look at two aspects here. The Q is transferred along the longitudinal direction as well as the Q is dissipated till this point, isn't it? But exactly at this boundary, I only have to account the conduction, no convection at all. So that becomes easy also, but and that is logical also, isn't it? Okay. Qmax, we were discussing Qmax. Qmax is a hypothetical concept which gives me what will be the maximum rate of heat transfer. Maximum rate of heat transfer is possible if I am having a maximum driving force at any location. So that is nothing but TW minus T naught. So what I am assuming that along the entire longitudinal direction from x equals to 0 to L, I am assuming the temperature of the temperature at location X, any location X in the fin is same as TW. So this TW minus T naught is the maximum driving force. In actual case, it will be T minus T naught. It will not be TW minus T naught. Okay. So this Q divided by Q max gives me the efficiency of the fin. So actual rate of heat transfer divided by maximum rate of heat transfer, assuming T equals to T naught, TW, that is going to give me the fin efficiency. So fin efficiency is directly obtained here. So this is Q divided by Q max, which is nothing but PL plus BW into H TW minus T naught. So here you can see this additional plus BW is coming in because now we are also accounting the heat transfer by this surface. Remember, while calculating for this particular element, we have not accounted because there is no surface exposed to the ambient. This surface is not the cross-sectional area of this is not exposed to the ambient. But when we are looking at the end of this fin, this particular surface is also exposed to the ambient, and therefore BW is also counted. So that is why PL plus BW is accounted here into H TW minus T naught. So this TW minus T naught get cancel out, and what we get is BWK zeta divided by PL plus BW into H, and in the bracket this entire bracket remains as it is. So this is a generalized expression. Remember, this is a generalized expression. Okay. Why I am saying it's generalized? Because we have used the convective boundary condition, but one simplified case of this also regularly used by the people. What people generally assume is when I move exactly, when I reach exactly to the end of the fin, that is x equals to L, we are assuming that the total amount of heat that is being conducted is already exhausted by the dissipation. So that means minus k dt by dx is equals to 0. Did you get it what I'm trying to say? I can go back to the figure again. So there is another simpler case people generally use. In fact, that is the more regularly used expression. You can find out in the books. I have derived a more generalized expression, but the more simplified expression I am just explaining you. So what is the assumption? Assumption is, as remember, we are moving along this x direction. So there is a amount of heat that is being conducted is reducing as we move along the x direction, because we are keep on dissipating the heat in the top surface, bottom surface, or the side surface. So by the time I reach to this particular end, which is x equals to L, all the heat that is being conducted is already exhausted by convection. So at this location, minus k dt by dx is equals to 0. That is what the assumption is, and it's a realistic assumption. It's not a uh, in a real case also, we in general wanted to design a fin in such a way that the total amount of heat that is being conducted till the end should be dissipated by the time it reaches to the end. So that's a realistic assumption, and based on that, my boundary condition changes. Remember, my boundary condition is now changes. X equals to L minus K dt by dx equals to 0. Remember, in earlier case, the boundary condition which we have used was minus K dt by dx is same as H T minus TA. That is what we have used. If you go back here, remember here, this was the boundary condition we have used. At X equals to L, we have used H T minus T naught. But instead of this, if we use minus K dt by dx equals to 0, I get a much simplified expression, and that expression is this. So if I put this in the original differential equation, what I get is T minus T naught divided by TW minus T naught, and that is equals to cos hyperbolic zeta L minus X divided by cos hyperbolic zeta L. Again, in a similar manner, we can find out what will be the amount of the total heat, the rate of heat transfer Q is obtained as BW minus K dt by dx at X equals to 0. So that becomes BW K zeta TW minus T naught. We can differentiate this equation with respect to X and put X equals to 0. So if we put that, what we get is BW K zeta TW minus T naught sine hyperbolic zeta L divided by cos hyperbolic zeta L. Again, the fin efficiency in this case can be obtained as Q by Q max. So Q max here, remember Q max is PLH. We have not used PL plus BW here. Remember, in this case, we have used PL plus BW, isn't it? But in this case, we have used only PLH. There is no BW term. Why? Because we are assuming that there is no heat dissipation from this surface, because by the time we reach here, my rate of the heat transfer by conduction is already exhausted by this end. So there is no heat transfer taking place from this surface at all. So there is no plus BW term. So what we get is, if you put all this equation, BW K zeta divided by PLH sine hyperbolic zeta L by cos hyperbolic zeta L. So this sine hyperbolic by cos hyperbolic can be represented as tan hyperbolic zeta L. And also this zeta is defined as zeta square is defined as PH by KW. Remember, we have defined this variable earlier. This variable we have defined here, isn't it? PH zeta square is PH by KBW, isn't it? So we can put it in this equation and rearrange the term. What we get is tan hyperbolic zeta L by zeta L. So this is a commonly used expression. If you look at several books, you will get only this expression. But the more generalized expression is this. More generalized expression is this. Okay. Is it clear to everyone? Is it clear to everyone? Hello? Hello? Hello?
Yes,
Yes.
sir.
Sorry, whenever I'm on the screen, actually I'm not able to see whether my team is working, MS team is working or not. So sorry. Okay. Again, one more simplification here is, remember what is P? P we have defined as 2B plus W, where B is the perimeter, isn't it? So very often the breadth of the fin is much higher compared to its width W. So W is small. In that case, P is equated to just 2B. If you put it in this equation, zeta square is 2H by KW, 2H, because this P will be given as 2B. So this BB will get cancelled out. So that becomes 2H by KW. In some cases, when the thickness is very small, we can use this value of P, which is the approximate, value of, this will give me the approximate value of zeta. Okay, clear? Okay, so this is all about the extended surface. Now let us move to another interesting concept. Okay. So another interesting concept here is a critical insulation thickness. What is critical insulation thickness? Why this word critical is used here? We will discuss. Okay. Now let us take a simple example that there is a pipe. In this pipe, the steam is flowing. If you look at the process industry, the steam is carried by the pipes, and these pipes are surrounded by the the insulations in order to reduce the rate of transfer to the ambient, isn't it? We wanted to reduce the heat loss. Now the question here is, if we suppose we are having a bare pipe, so and in order to reduce the heat transfer on this bare pipe, the insulation is wrapped. uh, as we increase the thickness of the insulation, what in general is seen is the rate of heat transfer initially, instead of uh, decreasing, it starts increasing. Just hear me out clearly. I am saying, as you put the insulation around the pipe which is carrying a steam, initially as you increase the thickness from 0, let's say, so initially the rate of heat transfer or rate of heat loss is going to increase by putting the insulation instead of decreasing, and it reaches to a maximum value and then it starts decreasing, something like this which is shown here. So initially as we increase the insulation, the rate of heat loss first increases and then it starts decreasing. I have not plotted it correctly. Maybe I just do it. Okay, let it be. Whatever qualitative information we wanted to give, that is anyway is clear here. Okay, actually this should be started from here. It should, this part should be lower than this. Otherwise you can argue why we wanted to put the insulation at all. Isn't it? So maybe just let me just correct it if it's possible. It's not possible. Okay, I will correct it. But you get it what I'm trying to say? Okay, just wait. Maybe I just do it. Now it is okay. Now it seems to be okay. Okay. So what I'm trying to say here is, as you increase the insulation thickness, first the rate of heat transfer is going to increase instead of decreasing, and it reaches to a maximum value. And if you further keep on increasing the insulation thickness, then the rate of heat transfer decreases. So why there is an increase? The question is why there is an increase in rate of heat transfer, because even though by putting the insulation, the rate of heat transfer by convection conduction is decreasing, but since the outer surface area is increasing, my convection rate is increasing, and therefore the overall heat transfer rate is increasing initially, but then it starts decreasing. Is it clear to everyone? Is it clear to
Yes, sir.
everyone? This is a very important concept.
Yes, sir.
So by increasing the outer surface area, by putting the insulation, my convection is increasing, and that increase initially is higher than the decrease by conduction, and therefore the total amount of heat loss first increases by putting the insulation, and it reaches to a maximum value. This maximum value is nothing but the critical insulation radius, critical insulation thickness, beyond which there is a decrease starts. Okay. Okay, so now we can obtain this critical insulation thickness for a cylindrical pipe wrapped with the insulation, can be obtained directly. So Q can be written as this is the expression which we are keep on using here. So here the pipe is carrying the steam or maybe hot fluid here, isn't it? So Ti is the temperature inside. Hi is the heat transfer coefficient inside. The radius is Ri. The outer radius of the insulation is R0. So R0 minus Ri is the thickness of the insulation. T naught is the ambient temperature and H naught is the heat transfer coefficient outside. The length of the pipe is L. Thermal conductivity of the insulation is K. Again, since the pipe is carrying a the liquid or steam maybe, but here the heat transfer coefficient inside the pipe is assumed to be very high. Heat transfer coefficient inside is assumed to be very high, and therefore the resistance accounted by this inside heat transfer coefficient is much lower compared to the other two resistances, conduction resistance here through the insulation as well as the convective resistance outside the pipe, and therefore this particular factor is neglected. So I may write down that for a clarity. Okay, I will write down this in the corrected one, which whatever I have said. So Hi here is much higher, and therefore the resistance corresponding to the heat transfer is much lower here, and therefore the factor corresponding to the inside convective heat transfer here in the pipe, that is neglected, and therefore the overall heat transfer Q is given as Ti minus T naught divided by ln R naught by Ri divided by 2 pi Lk. So this is nothing but the conduction resistance plus 1 upon H naught A naught, that is nothing but the convection resistance outside here. So in terms of in terms of radius, outer radius, we can represent this equation as 2 pi L Ti minus T naught divided by ln R naught by Ri by K plus 1 by H naught by R naught. So this is the expression we have obtained. Now, since we wanted to find out the location, or we wanted to find out the radius at which this maximum is going to occur, what we have to do is we have to differentiate this particular equation with respect to R naught and then equate to 0. So by differentiating with respect to R naught, this is the differentiation, and equated to 0, what we get is 1 by K R naught minus 1 upon H naught R naught square equals to 0. So based on this, the R naught is obtained as R naught critical, that is obtained as K by H naught. So in case of cylindrical pipe, the critical insulation radius is obtained as K by H naught. Okay, and what will be the critical insulation thickness? The critical insulation thickness will be K by H naught minus Ri, because Ri is the inside radius here. So that is going to give me the thickness. Again, if we differentiate this equation twice, what we get is this d square q by dr naught square is less than 0. So clearly this gives me a maxima here. That is what is clear from this. One more point to note down here is, in some cases, remember the questions are generally given like they will be giving you the heat transfer coefficient and the thermal conductivity, and one has to calculate the critical radius, isn't it? Critical insulation radius. So here K by H naught, that we can calculate directly, but sometimes what happens, this K by H naught comes out to be lower than Ri. So in such cases of insulation, critical insulation thickness does not exist. That is what it means. So what it means is the conduction resistance is always higher than the convection. um, uh, Whenever you are putting the insulation, whatever the decrease in the conduction rate is, that is higher than the increase in the convection rate, and therefore no critical insulation thickness exists in such cases. Is it clear to everyone? Hello?
Yes, sir.
Yes, sir.
Okay. Again, one more thing is that in the book, if you look at the critical insulation thickness for the spherical case is also obtained for that is an unsolved problem, but that you can do a similar analysis and you can find out the critical insulation thickness for the sphere. If I'm not wrong, that comes out around 2h by r, if I'm not wrong, but I don't remember clearly. But that you can do in a similar manner. Okay. Okay. Now coming back to another interesting concept. economic or optimum insulation thickness. Remember here we have looked at the critical insulation thickness beyond which there is a heat transfer decreases. But now we are looking at, see here beyond this point my rate of heat transfer decreases, but does it mean that I keep on increasing the insulation? If I keep on increasing the insulation, my rate of heat transfer or heat loss is going to decrease here. But then there is a cost associated with the insulation, isn't it? So I wanted to find out the thickness of the insulation which will give me the maximum return, isn't it? I should not keep on increasing the insulation thickness to infinity just because it is going to decrease my rate of heat transfer, isn't it? Because there is a cost associated with this insulation, correct? So let us find out what will be the economic or a optimum insulation thickness which is going to give me the maximum return or lowest cost, isn't it? Okay. So before we start looking at the analysis, if we increase the insulation thickness above the critical thickness, the heat loss is reduced. And as the heat loss is reduced, obviously the reduction in the heat loss is also saving in the energy lost. And the cost of energy lost is also decreased here. But at the same time, the insulation cost is increasing. So higher cost is incurred for the insulation. Okay, now these two factors has to be balanced and one need to find out a optimum insulation thickness which balances both these factors, isn't it? Correct? So the economic or optimum insulation thickness is that for which the sum of the insulation cost and the cost of the heat loss is minimum. So the cost is minimized here. So different factors which are important when we are finding out the economic or the optimum insulation thickness are the fixed cost of insulation, variable cost like maintenance cost, what is the service life of insulation, how much depreciation takes place, and the different taxes. Okay, these are the different factors which are important when we are looking at the economic or optimum insulation thickness. So let us look at a simple example again. There is a consider a case of insulated pipe carrying a hot fluid. Here Ti is the inside temperature, T naught is the temperature of the ambient, H naught is the heat transfer coefficient with ambient, R naught is the outer radius of the insulation, Ri is the inside radius of the insulation, K is the thermal conductivity of the insulation material wrapped around the this metal pipe. Okay, and the length is given as L. Again, what are the different factors? H naught is a film coefficient at the outer surface. It is defined as a K kilocalorie per hour per meter square per degree Celsius. So you can have a SI units also, but depending on if you use it in a SI unit in a kilocalorie, you will get it in kilocalorie units. The values you will get it in kilocalorie units, and per hour is there, isn't it? Meter square degree Celsius. Again, thermal conductivity is defined as kilocalorie per hour per meter degree Celsius. The cost of the insulation is this is the factor associated with the cost of the insulation. So that is just C. CH is the cost of energy. So whenever I am saving some energy, how much that is transformed in terms of money, that you can directly obtain by multiplying this cost factor CH to that. I is the interest rate, N is the insulation life, T naught is the ambient temperature, and Ti is the pipe wall temperature. Ti is the pipe wall temperature. Okay. Okay. Now let us look at different factors here. The inside heat transfer coefficient. Let us define the overall heat transfer coefficient in terms of the inside surface area. Inside surface area, and also let us assume that the HI here is a very large value, and therefore the resistance offered by HI is negligible, and therefore UI is given in terms of the conduction resistance through the insulation as well as the convective heat transfer with the ambient, and also there is a metal wall, but the conduction resistance offered by the metal wall is neglected. Okay, and also the thickness of the metal wall is assumed to be 0. Assume to be very small. Okay. Okay. So UI is nothing but the overall heat transfer coefficient based on the inside area is given as 1 upon Ri ln R naught by Ri by K plus plus Ri by H naught by R naught. And this is defined in terms of the inside area, inside surface area. Okay, so the rate of heat loss is given as area, which is nothing but 2 pi RIL into UI into delta T. So this becomes Ti minus T naught. Remember, Ti is the metal wall, the wall temperature, whereas T naught is the ambient temperature. So that we can write down UI Ti minus T naught. Again, here the rate of heat transfer, remember here this overall heat transfer coefficient is given per hour, isn't it, per hour. So that means we have to multiply it by total amount of hours there, and also we are calculating the rate of heat loss per year. So that means 24 hour into 300 is multiplied here, because we are assuming 300 working days in a year. Okay, so Q is obtained as area into UI into delta T into 24 into 300. So that is going to give me the rate of heat loss per year. Per year is a very important. Okay, is it clear to everyone? Similarly, the cost of heat lost, cost of the heat lost is again given as this Q. Remember, this is the amount of heat loss per year multiplied by the cost factor, that is going to be the uh, amount of money that is being lost because of the heat lost, isn't it? So Q into CS, that is going to give me the cost of heat lost. Now this is the cost of heat lost per year, but now there is a service life of the insulation, let's say for n year, isn't it? So we are comparing it at the end for the entire service life of the insulation. So the if I is the fractional annual compound rate, the present value of the heat loss Pi can be obtained directly by using this particular formula, which sums up the heat loss over the entire service life, and it also accounts the compound interest based on the compound interest that will be there. So 1 plus I is the rate of interest, and raised to the power j, where j is varying from 1 to n. So n is the service life here. So P1 is going to be the total net present value over the n years, Okay. So this is the present value based on the amount of heat lost. Now there is another factor which is nothing but the insulation cost. So insulation cost, remember, in general the insulation is purchased in the form of volume, in per volume basis, and then these are wrapped around the pipe, isn't it? So let us calculate the volume of the insulation first. So volume of the insulation can be obtained directly as pi r naught square minus Ri. R naught is a outer radius, Ri is a inside radius, into L. So that is going to give me the volume of the insulation applied, multiplied by the cost factor, associated cost factor, which is the C. So that is going to be the present value of the insulation. Now these two costs are added, that will give me the total present value. So that becomes PT is obtained as P1 plus P2. So this total becomes this. Again, here Q can be replaced by this particular equation, where UI can again replaced by the earlier equation here. So by putting all this, finally what we get is CH in the bracket summation 1 to n 1 upon 1 plus I raised to the power j, in the again multiplied by 2 pi RIL into UI. So UI is given as 1 upon 1 upon Ri into ln R naught by Ri by K plus Ri by H naught R naught, and this bracket close, multiplied by temperature difference, that is Ti minus T naught into 24 into 300. So this first factor is going to give me P1, that is the present value of the cost of heat loss over the n years, plus the insulation cost, that becomes pi R naught square minus Ri square into LC. Now we have to find out the value of Ri, which is going to give me the minimum value of PT. So what we have to do is we have to differentiate dPT by, we have to do dPT by dR0, and we have to equate to 0, and based on that we have to find out what will be the value of R0, the optimum value of R0. So that is what we have to do here. Optimum insulation thickness is obtained by putting dPT by dR0 equals to 0. And since this equation is little bit complicated, usually the optimization techniques are required to solve this. And typically, if you look at how individual costs are represented here, so P1 is going to decrease with increase in the insulation thickness. Similarly, the P2, which is nothing but the insulation cost, which is going to increase as the insulation thickness increases, and the optimum can be based on the total of these. So optimum is around here, which is nothing but the economic insulation thickness, which can be obtained by solving this differentiation. Okay, is it clear to everyone? If you are not able to understand many things here, the next tutorial is on this. So probably you will appreciate more the concept of this economic insulation thickness in the tutorial. Okay. So we stop here unless you have any doubt, any question to ask.
So could you please upload the tutorial sheet for the same?
Yes, I will do it. Thank you for informing. I will do it today. Yes. Thanks.
Thank you, sir.
So there is one more topic left in this particular chapter. Maybe we will cover it in the next class. Two more slides are there. Anyway, we will cover it in the next class, and then we will start with the forced convection. So the chapters we are looking at after this is forced convection, natural convection, then boiling and condensation. After that, radiation we are going to look at radiation, then heat exchanger units and evaporator. So these are the topics which we are left with. Okay. So we stop here unless you have any question to ask or any doubt is there. Again, one more thing. Okay. So when we will be having the quiz, that is what we wanted to discuss today, isn't it? Monday on 8th.
Yes, sir, for 8th.
So 8th we can have it in the class time. So that will be on the Moodle. Okay.
Okay, so like the first way you mentioned that will be objective based, linked questions one to each other that way.
It will not be objective based. It will be subjective. I did not say objective. It will be a linked question.
It will be numerical based. It will be numerical based, right? We'll have to type in numbers on Moodle.
Yes, you will have to solve, and based on that, each one of you will have a different answers. And these are linked questions. So depending on whatever you have solved in your previous part, the same answer you have to use in the next part. So if you copy it from some other friend, you will get 0. So that Moodle automatically recognizes that. Okay. Is it clear?
Yes, sir.
So that is why the linked questions will be there, so that in these unproctored examinations, some sanctity should be there, isn't it? So at least those who are preparing seriously, they should get some advantage, isn't it? So we stop here unless you have any doubt, anything you wanted to say.
And sir, how about the syllabus for that quiz?